be recorded. Please turn off your video now. And let me remind you that we still have plenty of time slots in the afternoon available for a meeting with Nico. So don't hesitate if you have time, if you're interested in signing up. And with that, I think we can leave it to Nico. Thank you.
Yeah, thank you very much for the introduction and for welcoming me here and for inviting me in the first place. It's very exciting that I can present you here the work that I've been working on for the last 1.5 years or so of my PhD. So the talk has the title Tracing the Onset of the AGN Feeding and Feedback Cycle, and what I'm going to present you is mostly optical IFU data and in a sense of the photon energy that might be the least energetic, high energy talk you've heard in a while. I hope can still enjoy what I'm going to present here. So the question that I and also you are interested in is what drives the rapid black hole growth. You might be aware of the discrepancy in the early universe where we observe quasars that are powered by several billion times solar mass black holes, and you have very little time to make them grow very rapidly to gain their mass that we observe in these high redshift quasars. So I asked the question, what are the host galaxy conditions that might be responsible for the super Eddington accretion that is required to bridge that gap? And in the nearby universe, we would like to understand what shuts off the growth of the black holes. That is the one part. And the other part of the question is, how does the accretion of the black holes in the centers of the galaxy affect the host galaxy? And I'm a member of the Close AGN Reference Survey, where we have a nice sample of 40 unobscured, so type 1 quasars, where we have a view of the central engine, and that stretches out to a redshift of about 0.06. Which means that we are probing a redshift range where we can still resolve the host galaxies. As you can see here on the left-hand side in the panels, the morphologies of the host galaxies, they're quite different from each other. But at the same time, we're capturing a luminosity range, which makes the sample comparable to the AGN that we can observe at a higher redshift. So in this sense, this survey serves as a reference to compare the higher redshift quasars with relatively nearby galaxies. Now, if you want to understand how the black hole growth and the host galaxy relates, you need to resolve this spatially, but also in the spectrum. And to do this, we have a number of instruments at different observatories employed, which range from the radio to the millimeter. And in the near infrared, we have nice observations, nice integral field spectroscopic observations from Gemini. But the core of the survey is the integral field spectroscopic data from the VLT that we acquired with the MUSE instrument. But also at a higher energy range, we have in the X-ray Chandra observations. Now, amongst the 40 AGN, I'm particularly interested in one of them, that is Markarian 1044. Markarian 1044 is a narrow-line Seyfert-1 galaxy, which is a peculiar type of the AGN population. And to recall this, I show you here the AGN unification model, which might be not up to date anymore. There are a couple of works that challenge the picture as we see it here, but just to recall how I have learned it in the lectures not so long ago. We have type 1 Seyfert if we see the broad line clouds with a high velocity circumventing the accretion disk, which eliminates the broad line clouds. And if they're obscured, we have Seyfert 2. Now, the narrow line Seyfert 1s, they have relatively low full width half maximum of their broad emission lines, which you could, in principle, achieve if you go to a very high inclination and you view this disk from the top. But there are a number of properties that make them more special, which is why we think that the population is indeed different from the type 1 population and cannot be only explained by an inclination effect. So the black hole masses that you compute from the velocity of the broadline clouds is lower than average. Okay, but they are also observed to have high accretion rates. And you see here in the spectrum that I showed for the source that I'll be talking about in the next hour or so, that there's strong iron emission from the broadline region, and that is a feature that is typically observed in the narrow line secret bonds. So in the X-ray, they also have, compared to the overall AGN population, typically a soft X-ray excess, and they are highly variable. So they are an interesting class of objects to study. The only caveat that we have is that in the nearby universe, they are relatively rare. So in this regard, Macquarie 1044 also stands out of the car sample due to its relatively low black hole mass, from which we compute Eddington ratios or accretion rates that are above the Eddington limit. Depends a little bit on the assumptions that you make for the broadline geometry and the way you measure the luminosity, but it's certainly highly accreting. So here in the panel on the left-hand side, you see the HST image, where you can nicely resolve the host galaxy. You see that on KPC scales, the morphology is a little bit diffuse. You see this tenuous spiral pattern. On few KPC scales, there's a bar in the center. And if you zoom in, you see that there's a circumnuclear spiral that only stretches a few hundred parsecs. And of course, in the center, you have the unobscured point source, which is the emission from the unobscured AGN. Now, as part of the close AGN reference survey, we have observed this galaxy with MUSE. The data from the wide field mode has already been analyzed in a work from Meredith Powell, where they found that there are no traces of AGN activity on galaxy scales, in the sense that there are no AGN-driven outflows that extend over several kiloparsecs, which is kind of surprising, given that you have such a luminous AGN. One would maybe expect that there would be some disturbance on the galaxy scales. It's not. And now we have also observations carried out with the narrow field mode, which is a novel mode of the instrument that has been active since 2019, and that really gives us the view around the nucleus. Now, whenever I say nuclear view, I mean that we can resolve tens of parsec scales. Here we have 30 parsecs. So we're still far from resolving the accretion disk. Okay. So in the first part of the results that I'm going to present here, I will focus on the host galaxy properties, because we would like to find out what host galaxy processes might be triggering the AGN activity in the center. And one very important thing that we need to take care of is the AGN emission from the center. Although the narrow field mode is assisted by the adaptive optics system, the point spread function has a finite width, which means that the very luminous source in the center that is unresolved distributes over the entire field of view here of the narrow field mode, which captures the core of the galaxy. And this is particularly important because the signal from the host galaxy is relatively faint if we zoom in so much. If you take, for instance, the 3 arcsecond aperture of the SCSS fibers and you observe the galaxy through the aperture, you have 70% from the emission coming from the point like AGN and 30% from the host. And of course, this ratio increases if you approach the center. This problem becomes even more dominant there. So we've used the software to separate the emission from the AGN that is called QDeplant. And yeah, this is a 3-dimensional problem because the point spread function has a 2-dimensional extent to the image plane, of course, but also depends on wavelength. So you need to understand what the wavelength dependency that is induced by the adaptive optics system is before subtracting this. And the result of this, you can see here. In the image plane, this is a mock image around the H alpha, where I integrated a small window before and after the subtraction. And in the spectral dimension, you can see the deblending here, where I integrated the 3 arcsecond signal around the nucleus. And indeed, you can see that the vast majority of the flux comes from the AGN. The AGN spectrum contains the AGN continuum and the broad lines. And the host galaxy then only consists of the narrow emission lines that sit on top of the continuum. So after the deblending, once we have separated the AGN from the host emission, we're left with 2 data cubes, and we can scroll through them. And once we approach the emission lines, you can see that the rotational field of the ionized gas within the galaxy becomes evident. I think it's most prominent in the H alpha that you can see here. And in the top, I show you the image that I extracted each wavelength along the spectral axis. Then the wide field mode that covers the entire galaxy, and the zoom in with the narrow field mode field of view. So the first thing you see when you approach the emission lines at the blue shoulder is the part that comes towards you. It's blue shifted here in the north, and then it distributes towards the south. It's this ring-like feature. Okay, we can not only produce videos from this, but we would also like to quantify what the emission line properties in the host galaxy are. And for this task, we have used the Pi Paradise routine, which in principle does the same as the PPXF. So it measures the line of sight velocity distribution of the stellar continuum and then fits the emission lines that sit on top of them, except that it has one technical advantage that you could see earlier in this slide. Here, the continuum of the stellar emission has some variations on large scales along the wavelength axis that are not physical. That's an artifact from the deblending process. And what Pi Paradise does is it first normalizes the stellar continuum and then fits the line of sight velocity distribution, which gives us a way more robust result. Yeah, and the outcome of this process is I show you here for a small aperture of f8 × 8 spaxels that I integrated. And here you can see that, yeah, the stellar continuum emission is relatively faint, which is just a result of that we zoom in so much into the host galaxy. But the ionized gas emission, the emission lines on top of it are still relatively prominent, which allows us to map the surface brightness of the strong emission lines that we have available in the optical. On the left-hand side, I show you the contours of the HST image here as a guide for the eye, what the spatial dimensions are that we're probing. So the structure here is the circumnuclear spiral that you could see in a few hundred parsec scales. For each of the strong emission lines, the first feature that pops into one's eye is maybe the bright blob in the center. I will come back to this later. For the moment, I would like you to focus on the ring-like structure around the center. And actually the ring, which appears to be very circular, is intrinsically an ellipse because the galaxy has an inclination of 67 degrees, which gives us an axis ratio of about 2.5. This is why we call this structure the circumnuclear ellipse. And the other parameters of the emission lines, like the first and the second moment, that tell us that the velocity of the ionized gas, the velocity field follows relatively smooth rotation. You can clearly identify the rotational axle, which has a little bit of a wiggle. And the velocity dispersion is relatively low. Now we can use the emission lines in the optical to identify the underlying ionization mechanism. If you apply this PPT diagnostic here and compute the flux ratio between the emission lines, there are these demarcation lines from Kaufman and Cooley, which tells you that the ionization field is not so hard in this regime, and the ionization parameter. And all the data points fall into that part of the PPT where the flux ratios are consistent with ionization by star formation, not AGN ionization. And remember, we are probing spatial scales that are very close to the nucleus. We're resolving about 30 parsecs from the nucleus, and yet everything that we see star formation ionized. First time I compiled this plot, I was surprised because I had this image in mind. Okay, when we have a luminous AGN, you would expect some signatures in this, either in the ionization pattern or at least in the kinematic patterns of the ionized gas, but except this block here in the center, there are no traces that are extending over galaxy scales. Okay, one thing I would like to highlight here is, again, if you look through the 3 arcsecond aperture and you compute the line ratios, you end up with this data point here, the star, which even more drastically falls in the star formation regime. So this is without deblending the AGN emission and without spatially resolving what's going on in the host galaxy. And from this, you would maybe conclude that the galaxy, because you do not resolve it, is not an AGN, but a star-forming galaxy, if it was, for instance, located at a higher redshift. So, might be that this galaxy is archetypal for a population of galaxies at a higher redshift where you can just not trace where the emission in the host galaxy comes from. Okay, so if everything is star formation ionized, we can compute star formation rates from the H-alpha flux, because we know the emission is caused by ionization to star formation. And we do this for the integrated circumnuclear ellipse for all the flux there, can correct this by the extinction, and then use a calibration between the H-alpha flux and the star formation rate. And this tells us that this structure around the nucleus has a star formation rate surface density that is in the starburst regime. So we have a circumnuclear starburst ellipse. It's contributing a significant amount of the galaxy-wide star formation rate. It's about 30% that's concentrated around the nucleus. We also compute the gas phase metallicity from calibration with the N2S2 index. And there you can see that throughout the structure, we have relatively homogeneous enrichment properties. We're probing 2 different timescales there. The star formation from the H-alpha is more sensitive to the recent star formation on timescales of maybe about 5 megayears, while the gas phase metallicity gives you more cumulative measure for the enrichment of the ISM. And it appears to be relatively homogeneous throughout the structure. And if we integrate this and compare the gas phase metallicity with the overall population of star-forming galaxies, we can see that Macquarie 1044 deviates from the relation by about 1 dex, sits on top of the relation, so it's metal richer there. And if we assume that the star formation will just continue as it does at present day, the galaxy will continue to diverge from the relation. Okay. Coming back to the star formation, I initially asked what processes might cause the AGN phase that we see in the luminous core of the galaxy. And we thought that maybe the star formation that is so close to the nucleus might be related to the activity. And to test this, we have done a very simple comparison between the mass injection rate that is caused by the star formation. So stars evolve. They go supernova, they inject winds, energy and momentum into the ISM, and we compute a mass flux rate from this by integrating over all the mass that is ejected by massive stars, except some remnant mass, and multiplying this with the star formation rate and weighting by the initial mass function. And for the integrated structure that you see here, assuming no inflows, no outflows, and a simple closed box model, we end up with a value for the mass injection from massive stars that roughly equals the present day black hole accretion rate. Of course, there are a number of assumptions going in here. For instance, the radiative efficiency here, and also no inflows and outflows, which might not be the case in reality, but I find it quite surprising that the 2 numbers match so well with each other. Now, of course, there's only a single case. It doesn't tell you that there's an actual causal connection, but there are more reasons why you should think that both processes are connected. There have been simulations carried out by Marta Volontieri in 2015, and they have used the Horizon AGN simulation to show that the star formation does correlate with the present-day black hole accretion rate. But only if you look around the nucleus of the galaxy. If you compare with the galaxy-wide star formation rate on a few kpc scales, there's no correlation between the two properties in the Horizon AGN, but only for the star formation on 100 parsec scales. And Maclaurin 1044 fits well into the correlation. So the line you should compare it with here is the blue lines, which are remnant galaxies. They are left alone. They have no merger, no companion, no signs of disturbances in the kinematic field. And the reason why we know this is we have carried out a kinematic modeling of the rotation that we see. So if you remember the host galaxy morphology, that was the disk-like, so we have used for the rotational field a thin disk model to reproduce it. Again, on the left-hand side, I show you the spatial scales with the HST contours. In the top row, you can see the wide field mode view covering the entire galaxy. And in the bottom, the use narrow field mode field view zooms in into the central region. And in the second column, the velocity field that we measure from the stellar continuum emission is shown. Right next to it, the model that we fit to it, which is a very simple model, doesn't use a lot of parameter except the rotation curve that it extracts out of it. And yeah, the velocity residuals are shown on the right-hand side here. And you can see that this simple model produces from the galaxy scales to the very nucleus the rotation quite well. And this is also the case for the ionized gas, which might be much more prone to the processes that originate from the AGN or from mergers or whatsoever. Also here you can see that there's a clear rotational axis, and you see that the model reproduces the data well. Only if we look again on structures of the circumnuclear ellipse, let me highlight this here, you see in the velocity residuals that there are some patches that approach us or are receding from us with respect to the kinematic model. I've integrated the structures here in the line flux, and I show the line shapes here. They are systematically shifted by about 10 kilometers per second, which is not much, but this could be a sign of ongoing black hole feeding that is triggered within the galaxy. If you really want to find out what the processes are, it could be the star formation that is happening in the ring here. But it could also be maybe gravitational instabilities caused by the bar that you could see earlier in the HST image, which has been shown to be able to trigger gas inflows towards the center. You need to have a look at the molecular gas phase, because the vast majority of gas that is accreted by the black hole is in the molecular gas phase. And the second reason is that the ionized gas that I've shown you here might not be the best tracer for the molecular gas, right? Because the energy that's injected from the AGN, but also from the stars in the star-forming ellipse around the center, might induce turbulence to the ionized gas phase. Okay, so there have been observations of this source carried out in November 2021 with ALMA, and they will reveal what amount of gas is channeled towards the center, and then also tell us what the process in the host galaxy, which must be intrinsic processes, triggers this gas inflow. Okay, this was the first part, focusing on the host galaxy. The second part will not be so long, and there I will focus on the outflow, the bright feature in the center that you could see earlier. So the outflow is not only visible in the image plane, that's the bright blob, but also in the spectrum. This is the highest signal to noise spectrum from the very center that I show you here. And you can see that we require multiple components to reproduce the H beta and H alpha emission line shapes. There's a broad component, obviously, because it's type 1 AGN, and several narrower components, but also there's this blue shifted wing component there. And that is also present in the O3 emission. Now this shoulder that this component produced in the O3 emission line shape is typically interpreted as a signature of an ionized gas outflow that is approaching you, and the receding side is just obscured by dust. From the kinematic modeling, we know the systemic velocity of the galaxy with a high precision. And this tells us that already the core component, so the narrow component, is blue shifted by 140 kilometers per second, which is kind of surprising because this narrow line is usually interpreted as the extended narrow emission that is in the galaxy frame. In this case, it turns out it is not. And the wing component has a velocity of 570 kilometers per second, so it's also approaching us with an even higher velocity. Okay, now this information we can use to trace the components in the image plane. We know what the kinematics are, we keep them tight, and we also keep the flux ratios that we measure here in this spectrum from the nucleus tight. We can produce base spectra and fit them to the spectrum that we have available in each of the spexels. And this technique is called spectro-astrometry. I show you here some mock data where I've tested this approach to trace each of the components, which we think are originating from intrinsically complex structures that are related to each other. So the broad emission line is point-like in the image plane because it's spatially unresolved. That's exactly what you see here. If you subtract the model, we end up with residuals that are essentially flat. And for the mock data, I have shifted the wing component by 1 pixel here. And then you can see that the model of the surface brightness profile I fit to it also reproduces the line shape and the surface brightness distribution well. So here we can say with high accuracy that this component must be offset by 1 pixel. And it turns out that this method works well down to an offset of 0.1 pixel, which corresponds to 1 parsec in the galaxy frame. Now, what happens if we apply this routine to the actual data from Karen 1044? Well, there we see that neither of the components has a significant offset from the position of the broadline emission. And this tells us that the wing component and the core component, both outflows, they are extremely compact in their projected size. They're smaller than 1 parsec. And there's more to this. There is not only an outflow that we see in the ionized gas emission, but also in Lyman alpha absorption. So there's this archival HST stiff spectrum, which I show you here. We've used multiple Gaussian components to produce the line shape here. And you see that on top of the Lyman alpha emission, there are several absorbing features. The most blue shifted ones here, they are not belonging to the host galaxy. They are foreground extinction, the Lyman alpha forest. But the feature 1 and 2 here, that are particularly interesting for the analysis that I'll show you here, they are local to the galaxy because they have a high metallicity because they're also identified on other absorption lines in the UV. So these must be local absorbing features. Okay. Turns out that the velocity that we measure there for the Lyman alpha absorbing features are higher than for the O3 emission. Yeah. So if you compare the slow and the fast component with each other, respectively, they are different by about a factor of 2. And if you compare the velocities amongst the Lyman alpha absorbers and the O3 emitters, respectively, they are about the same. So this coincidental measurement led us to the idea that maybe the structures that we probe with this are related with each other. And maybe you can explain the velocity difference with a geometric model. Now, the O3 emission that we see in the spectrum, but also in the image plane, they must come from a region that is intrinsically extended. If you make it too compact, then the gas densities get too high, and then the atoms collisionally de-excite, you wouldn't see this line in the first place. So there must be an intrinsically extended structure that emits in O3, whereas the Lyman alpha absorption, as they sit on top of the Lyman alpha emission, they probe the absorption directly along the line of sight towards the broadline region. So our idea was maybe there's some expanding structure, an outflow that we described by this shell cap, and only part of this O3 emitting shell cap is responsible for the Lyman alpha absorption directly along the line of sight, which would explain why we observe the higher velocities here, because the O3 emission we integrate over the structure, which is inclined, and we only see the line of sight component. Okay, so we use 3 parameters to parameterize this geometric problem. We have one, of course, the most important is the inclination, but also we use a concentration to describe how jetted the outflow is. We make this alpha, which is an angle in fractions of the half opening angle of the outflow. If you make this smaller, you make it more centrally concentrated. And as a third parameter, we of course have the flux ratio. Because we have 2 expanding shells, we can vary how intense the emission from each of them is. And our goal was then to explain maybe the O3 blue shoulder emission line shape that you see here. It's not so well described with the 2 Gaussians that we have used earlier. Maybe this expanding shell model does a better job there. And to give you a little bit of feeling what each of the parameters does, if we incline the system, the 2 components in the spectrum move closer to each other. The second thing I vary here is the flux ratio between the 2. And the third parameter is how jetted the outflow is. If we make it more centrally concentrated, each of the lines has a smaller fluid maximum, obviously. And then the integrated line shape that you see here as a black line, we fit to the O3 line shape observed in the spectrum. Okay. What are the predictions from our models? Well, it predicts that the inclination is very high. It's above 80 degrees, slightly. Has an uncertainty of about 5 degrees, and it's relatively concentrated. But the inclination that we measure there, 80 degrees, is a little bit difficult, given that we have a type 1 AGN. We have an unobscured view to the central engine. And I would expect at some point, if we stay in this dust torus model, if we incline the accretion disk too much by more than maybe 55 or 60 degrees, which is the half opening angle distribution of the type 1 AGN, we would just obscure the view to the central engine. So either of the 2, the dust torus model or the expanding shell model that we put in there, cannot be true in the assumptions. So I think what is going on is just that the assumptions of our model, that the Lyman alpha occurs in the same structure as the O3 emission, is just not true. Okay, so the ISM on the subparsec scales that we are able to resolve with Mu's narrow field mode must be more complex than the simple picture that we have put in there. Okay, so this outflow model does not work in its prescription. Okay, so I can conclude at this point that what we have learned from studying this single case of a highly accreting AGN, Macquarien 1044 is a young AGN in the sense that we do not observe any disturbances from the AGN on host galaxy scales, even very close to the center, down to 30 parsecs. There is a lot of ongoing star formation close to the nucleus and no signatures of an extended outflow, neither in the kinematics nor in the ionization that we measure. So in this regard, Macquarien 1044 as a narrowline C41 galaxy could be archetypal of a galaxy population at a higher redshift that's just rapidly growing, but are not identified as the AGN as we see them in the local universe. And we have seen for this example that the nuclear star formation can explain from a simple mass budget consideration the high black hole accretion rate. Okay, and the third last point that I would like you to take away from this is a technical thing. If you want to understand how the black hole accretion in the center and the host galaxy, how they relate to the property, it's very important to consider the spatial scales. If you learn something from this, you need to know where in the host galaxy the emission that you are studying comes from spatially. Okay, thank you.
Thank you so much. Thank you so much. Very intriguing. So, do we have any question from the?
Yeah, a couple of questions. First of all, the technical question is like more scientific. Let's start with the scientific, but short. What makes you think that it's an oval, that it's an ellipse in the disk, and not a warped structure? So basically, a misaligned nuclear disk, which you see almost at John. Well, it's not almost at John. It's like 30 degrees according from if you judge from the inclination. So why do you think that it's aligned with this 67 degrees comes from the larger scales?
Yes, so the kinematic modeling has been carried out already in the first paper that I've mentioned from Powell in 2018. They've used the stellar rotation, and they traced the rotation curve within the galaxy. And from the shape of the rotation curve, you can conclude on how the galaxy inclination intrinsically is. That doesn't tell you, I agree, on the inclination of the structure there. That's just the assumption that it follows the velocity field. Okay.
Because it can be misaligned.
Can be misaligned, yes. Might be the case because it's just coincidental that it appears so circular, right?
You really need to stretch the potential, and bar doesn't reach the
Yes.
to get it elliptical. And second question is technical. Muse and FM is low Strel, so you have like 95% of the PSF of the energy, the broad PSF component. So it's only a peak that you're probing. So it meant that you really need to make to do proper modeling of kinematics. You really need to know the underlying distribution of density for every emission line. So basically, if you have a structure, I saw in your movie when you scroll through the tube, around 03, for instance, there was this very funny structure, spatially resolved on like large scale, and so this thing actually can affect what you measure because it has the atmospheric seeing. It's like 0.6 arcsecond that goes into the tube. So how did you take this into account? Because if it's an elliptical galaxy with a point source in the middle, that's trivial. But here, nothing is trivial. It's like weird with all these nuclear disks spiral out and globes and so on.
Yes, that's very true, and a very important point. You need to subtract the PSF with a high accuracy, and you need to understand this. We do not do it in the way we do this. We see that the PSF subtraction affects our results. And to do this, I can maybe show you on another slide. We use an approach where we capture the empirical PSF in the center with a high signal-to noise. And for the outskirts, we use an analytic model, which turns out to describe the turbulent halo of the PSF quite well, that you can see here in this slide. So along the spectral axis, we only have 3 positions available where we can measure the PSF, because we have a point source from the nucleus, right? That's a broad line emission, H beta, H alpha, and a line that's blended here. I think it's calcium with something else. It's even redder.
It's partial line. It's one of the higher partial lines.
Yeah. So 3 broad lines. There we extract the empirical PSF, and because the signal to noise gets relatively poor if you go away from the center, we have an analytic model that describes the PSF shape there. Well, then we construct this hybrid PSF and interpolate this along the wavelength axis. And this approach, compared to the individual ones, turns out to perform better and produce robust results. Also in the ionized gas kinematic.
And then you inject it in the mold, right?
Yes.
Thanks. More questions from people here? No. Did you see any question from online? I might have a very trivial question about your second part of the exponential model. So do you incorporate, for example, the local density into the flux ratio? Is the local density likely to be a relevant parameter when you fit the with the exponential model?
So let me go back to this slide. We didn't include it as a parameter in this model because I think the signal to noise of the emission lines would not allow to include any fourth parameter.
Oh.
But I agree that the density that we see in the center is very important. And in fact, if we at the signal to noise that we have there, we cannot see any S2 emission that belongs to the outflow, which means that the gas densities must be higher than something 10 to the 3. And also there is only very faint N2 emission, which could tell us that the outflow is very dense that we see there. So it's not only compact, it's also very dense. And that needs to be considered if we trace the emission close to the nucleus. Yeah.
Okay. Thank you. Okay.
One more short question, like follow up to yours. So you mentioned that it's pretty dense, where the density is higher than we looked out from. Do you see it in coronal light? Because I saw that the galaxy has coronal forest AGN. So you have all these weird ionization lines that originated this intermediate density, like 10 to the 2 to 10 to the 5, basically. And you might be able to detect it there. So
Okay, I haven't checked yet.
Because this, I mean, this stuff like iron 10 or iron 7.
Yeah.
There are a few of them, and you see them. This is not a very typical for an AGN trip. These are rare.
Yeah.
Okay. We don't have more questions. Like we don't have pizza yet, so we need probably to wait a few more minutes. But let's thank our speaker again. And, thank you for coming. Thank you for the great talk.